All right, boys and girls, so today we're going to be going over lesson 8, which is modeling using three-dimensional solids. I'm going to start off by reading the do now. So part A says, what similarities do the cross sections that are parallel to the base of the pictured figures have? So I'm just going to highlight, usually like we always do, what's important. So what's going to be similar between the cross sections that are parallel to the base? So if I look, I already took a minute to just already outline where those cross sections that are going to be parallel to the base would be. So I know I can take a cross section that's either horizontal, like I did here. I could take a cross section that's going to be perpendicular, straight up and down, or I could take a cross section that's going to be diagonal. All right, so there's a few different types that I could cut out, but I specifically want the one that's going to be parallel to the base. So it has to be going like horizontal with the base here. Same thing, horizontal with the base here. So what similarities do these cross sections have? Well, if I look, I can see that this is five-sided polygon, which makes it a pentagon. This also is a five-sided polygon, which again would make it a pentagon. So what similarities do they have? They're the same shape because they're both pentagons. If we look at part B, it says what differences do the cross sections have? So again, I'm just going to highlight that. What differences do the cross sections, again, that are parallel to the base? It's those specific ones that we're looking at. What differences do they have? So when you first look, you're probably thinking, I don't think they're different at all because they're the same shape, but really they are going to be different. I'm going to call this like picture 1, and I'm going to call this picture 2. Okay, so if I look at the first picture, I can see that it's going to be the same size pentagon all the way through. So you know what? Let's write that first. Same size pentagon all the way through. And what I mean by that is if I took this pentagon in the cross section and I elevated it like down or I brought it up, it's going to be that same size all the way through. Nothing is really changing about it. But if I look at picture 2 here, this pentagon is going to get larger as I go further down towards the base. Or the same thing, it's just going to get smaller the further up I bring it to the top. So again, I'm just going to write that down. So what's different like in picture 2? The size of the pentagon changes depending on its position. All right. Before I keep going, just remember if I'm ever talking too fast, if I'm doing too much, please pause the video to take a minute and try to really think about what it is we're going over here before you continue on with any further questions. All right, so again, what similarities do these guys have? They're the same shape. What differences do they have? Well, this is going to stay the same size and shape the whole way through. This will stay the same shape, but the size will change depending on where it is. All right, moving on to example 1. It says a water cup is in the shape of a cone. So I'm just going to highlight that. Anytime they tell me the shape, I love that. I like to just keep that highlighted so I remember it's important. I know that the height is 18 inches. And I know that the diameter is 12 inches. So I'm going to stop and just write that on the side really quick. I know that the height, I'm just going to use H, is 18 inches. And we had gone over that whenever you see a number with a unit, you should really get in the habit of underlining it. Super important because if the units don't match, you know you have to do some work before you can just plug in. Again, I see that the diameter is 12 inches. So far we're good. The units are matching, but we never use diameter. We always use the radius. That's right. We use the radius. So I'm going to take 12 and cut it in half, and I'm going to make it 6 inches instead because we never use diameter. All of the formulas use radius. So I know the radius is 6 inches. If I continue reading, now it says, what is the volume of the water in the cup? So what is the volume? That's going to be the question here. I have to find the volume of the cone, but it specifically says I not only have to round to the nearest tenth of a cubic inch. So again, my units are matching, so I'm good to go. But I want to know how much water is in there when it's only 1/3 of its height. So I could either find the volume of the entire cone, or I could find the volume of just 1/3 of the cone, which is what we're going to do for this question because that's what it's asking. So I'm going to start off by just writing the volume formula of a cone, which is 1/3 pi r squared h. I know that whenever I'm plugging in, I have to use parentheses to do it. So I'm just going to do like r squared times h because I know I'm going to plug some numbers in there. This is so unbelievably important, so please make sure you are listening carefully here. If I want to find 1/3 of the volume, because I only want to find 1/3 of the height of the cone, I know that this radius up top, you know what, let me keep the blue. So sorry, guys. So I know that this radius from the question is 6 inches, right? But I don't want the radius using, again, the entire cone. I only want 1/3. I'm hoping you guys are able to see this. These radiuses, or really radii, are not equal. This is definitely a longer line. This is definitely a shorter line. So I have to now find, well, what is 1/3 of 6? Because I'm not going from top to bottom. I'm going from 1/3 of the top to the bottom. So on the side here, I'm just going to take 6 and multiply it by 1/3 because I only want 1/3 of the radius, not the entire thing, which becomes, here we go, the number 2. All right, and then over here, same thing. I don't want the entire height because the entire height, let me just plug this in here, would have been 18 inches all the way through, but I'm only looking for 1/3 of the height. So if I multiply by 1/3, I get 6. So I'm just going to add that to my picture here. This height is 6 because, again, this is really the cone that I'm looking for, not the original. So now I'm going to go ahead and plug everything back in. So the radius I'm using would be 2, and the height that I'm using would really be 6. And then when I type this whole thing into my calculator, I should be getting 25.13 inches cubed, but I want to round to the nearest tenth. Don't forget to reread the question. So I know that there's only 1 0 in the number 10, so I only want to go one place after the decimal, and this isn't going to round up, it's just going to stay. So it's going to be 25.1 inches cubed. That would be our final answer for example 1. Okay, moving on to this bad boy example number 2. So as I read number 2, it says the water tower in the picture is modeled by the 2-dimensional figure beside it. So I know that a water tower is literally holding water, so that makes it a 3-dimensional shape. Just like a bottle of water. It's 3-dimensional because it's holding some type of substance. This picture next to it, they're saying, is a 2-dimensional shape. Just so that we can kind of see what those units would look like for as far as like how tall this shape is, what this length would be. They're just changing it from a 3-dimensional shape almost to a 2-dimensional shape, just so we can see those numbers nice and clear. The water tower is composed, grab your highlighters, of a hemisphere, that's important, a cylinder, important, and a cone. Again, anytime they give you a shape, I always like to highlight it. Then they're telling me that I'm going to let C be the center of the hemisphere. I'm going to underline that. It's really important. C is the center of the hemisphere. And I know that D is going to be the center of the cone. So D is the center of the cone. If I jump down to the bottom, they're telling me that line segment AC is 8.5 feet. So I'm just going to underline that to make sure all my units match. 8.5 feet, it's already here. BF is 25 feet. So again, my units are matching. BF is 25 feet. And I know the measure of angle EFD, F is in the middle, so it's the most important, is 47. 47, it's already marked. I have to determine and state, so again, I always underline the question, determine and state to the nearest cubic foot. As soon as I see cubic, that tells me immediately I have to find volume. So I know they're telling you to find the volume, but they didn't have to, because by just using the word cubic, that means find the volume. Again, cubic feet, so it's all matching, I'm good, of the entire water tower. So if I look at the water tower here in this original picture, there's 3 shapes that are making it up, which they told me in the diagram up top. I know that there's going to be a hemisphere, which is down below. I know that there's a cylinder, which is in the middle, and I know there's a cone, which is up top. So since I'm going to find the volume of all 3, and then I'm going to add them together at the end, because again, I want to find the volume of the whole shape, I just went ahead and just wrote what those formulas were to kind of start us off here. Super important, when you look up hemisphere, it's not there. So just as a reminder, you're only going to see the word sphere on your reference sheet. You need to remember that a sphere would be like holding an entire basketball. I don't have the entire basketball here. I only have half of it. So you got to take that and cut it in half. All right, moving on. So now if I continue solving, as I look at the cone, just because it's the first shape that I wrote, I know I have to plug in the radius and the height to find the volume of that entire shape. So if I look at the cone, which is up top here, right now I don't know the radius, and right now I also don't know the height. So I can't really start with the cone, so I'm going to move on to the cylinder. I know to plug in for the cylinder, again, I need the radius and I need the height. So if I look at the cylinder here, I don't have the radius on any corner, on any side here. And I also, I don't know, maybe I do have the height for the cylinder. I guess I do. So here's my cylinder, and I can see that the height of the cylinder is 25 feet. So I could fill in the 25, but it's not really enough. So I'm going to actually ignore the cylinder for right now and see if I can at least just get the hemisphere and kind of go from there. So the hemisphere looks the simplest because I just need the radius and I'm good to go. So if I look at my hemisphere, I'm like, okay, I see 8.5 is in there. All right, let's start working with that. This is where the wording of the problem becomes so important. If I know that C is the center of the hemisphere, I'm just going to actually highlight this in blue for a second. If C is the center of my hemisphere, I know that a hemisphere is really a circle, right? Like a basketball, a soccer ball, dodgeball, anything like that. It was just cut in half. So I know that from the center to any point on this quote unquote like circle is considered to be a radius. So I know that this distance right here from the center to a point on the circle is a radius. So that means C to K is a radius. C to B is also a radius. So I can go ahead and say, if this distance is 8.5 feet, I know this distance is also 8.5 feet. And I know this is also 8.5 feet. All right. So now that I really do know my radius, which is the center to a point on the circle, any of these would have been a radius, I can plug in and at least get the volume of the hemisphere. So I know again that volume is 4/3 pi r cubed. I know that my radius is 8.5, but I'm only finding a hemisphere, so I have to divide by 2. You would type the whole top in and press enter, then you would divide by 2 and press enter again. You should have got 1,286.220,392 ... right? We have a bunch more numbers after that. I can't round yet because this is not my final answer. You only round when you're about to be done. So I'm going to leave it here and kind of move on. So now I'm just going to work my way back to the cone and then just kind of start again. So if I look at the cone here, I know that in order for me to find the volume, I need the radius and I need the height. So now I'm seeing, okay, well, I need the radius of the cone, and it tells me here that D is the center of my cone. So just like I said down here, I know that any radius is from the center to the edge. It's from the center to the edge. So I know that if this distance here is 8.5 feet, I can just kind of elevator it up and say this is also going to be 8.5 feet. The only reason I'm allowed to do that is because this middle shape here is a cylinder. So I know in a cylinder, it's the same diameter or it's the same radius all the way through. So if this is 8.5, this has to be 8.5. Just like a can of soup or a can of soda, it's got to be the same circle all the way through. All right, so I know these have to match. So now if I want to plug in for the cone, I'm like, okay, cool. I have the radius, so let me plug that in. Volume is 1/3 pi times the radius, which is 8.5 feet. So I have 8.5 squared times, I still need the height. So I know that heights are perpendicular with the base. So I'm just going to like highlight this out again a little bit for you because it's kind of glim here. I know this is already a right angle because it was marked originally, but it has to be a right angle because again, heights are perpendicular with the base. So since this is what I'm looking for, I'm just going to throw an X on here for right now to remind myself that that's the goal. I don't know if you're seeing this, but I now have two right triangles. I have this guy on the right. If I bring that 90-degree angle over, I have another right triangle on the left. I'm going to work with the one on the left since that's where the information is and go from there. Anytime we're looking for the missing side of a right triangle, we use Pythagorean theorem. That's the a squared plus b squared equals c squared. But I don't have enough information right now to use that. I would need at least two sides here, and I only have one, so that's not enough. So the only other option is for me to use trig, which is SOHCAHTOA, that unit that we just learned, I think, kind of right before all of this stuff had happened. So if I want to use trig here, I have to use the angle that they gave me, which is the 47. It's got to be one of the acute angles. So I'm going to use 47. I know that X would be the opposite side, and I know that the 8.5 would be the adjacent side. I'm just going to put those in parentheses there. So if I were to write SOHCAHTOA, I'm just going to add that to the top of my paper here. Let me move this down so you guys can see. SOHCAHTOA. I don't know why this always reminds me of Finding Nemo, like SOHCAHTOA, SOHCAHTOA when they're in the fish tank. Okay, back to it. So if I look down below, I know that if I'm using the opposite and the adjacent, O and A, that would be the tan function. All right, so on the side here, I'm going to set myself up. So I'm really finding tan of 47 degrees, and tan is opposite over adjacent. Opposite is the X, adjacent is the 8.5. I'm going to turn this into a proportion. So I'm going to put that baby over 1, and then I just cross multiply and solve. So when I cross multiply, X times 1 is X. And then this is what you're going to type into the calculator. You're going to do 8.5 times tan of 47. All right, when you type all of that in, you should be getting 9.115134 ... because there's a bunch more decimals after that. But again, this is not my final answer. I'd have to find the volume of the whole tank. This is just helping me do that. So I have to keep every single digit. So down below, I'm going to plug that in now. So again, we said it was 9.115134.035. All right, that's all of the decimals that at least I can see on my calculator. If you do not have a calculator, that is fine. You just have to take your phone and turn it to the side. And when you look at it, you're going to see that you have the tan, cos, and sine functions already there for you. You can do basically anything on that calculator except graph. All right, so try to use that for now. And if not, just go with my answer. If you're having a hard time, this is what you should have got when you plug this in. All right, so now if I go back to my calculator and I type all of this in at one time, I got that the volume was 689.651251.4. All right, and again, I'm not done. It's not my final answer, so I have to keep the whole thing. Whew, all right, last but not least, we got to do the cylinder. So hopefully this will be a little bit easier. I don't know if we're going to have to do any work here. Hopefully we're done with that. So for the cylinder, which is the shape right here in the middle, I have to find the radius and the height in order to plug in and be done. So if I look, I can see that the radius is from the center to a point on the cylinder, 8.5. From the center to a point on the cylinder, 8.5. So I know it's got to be 8.5 for the radius. I'm going to plug that in. Again, you're always plugging in using parentheses. And now the height of the cylinder, well, the cylinder is right here in the middle. It's just that little chunk from the top to the bottom. I'm trying to make sure my shadow isn't covering this up. So the height is 25. Again, you would type this whole thing into your calculator. You should have got 5,674.501731. And now in order for me to wrap this question up, to find the volume of the entire water cone, I'm going to take the volume of the cone, I'm going to add it to the volume of the cylinder, then I'm going to add that to the volume for the hemisphere. I'm going to put all three shapes together, and I should have gotten 7,650.3. But I'm about to be done. This will be my final answer, so I can kind of stop at the 3 and look back. I want the nearest cubic foot. So I really want the nearest whole number. Is it 760 feet? 51 feet, something like that. So this will not round up. It's going to stay. So it's 7,650 feet cubed because we're finding volume, and volume is always cubed. All right, please go back and feel free to rewind, pause, relook at anything if you had any questions about where I'm getting those numbers from. This was definitely a really challenging question. It was a Regents question. Okay, moving on. So now we're on example 3. I'm going to pick up the pace just a little bit because I know that kind of took a little while. So it says a candle maker is using a cylindrical mold. So I'm going to highlight cylindrical. That means it's a cylinder to make candles. The height of the candle is 13 centimeters. So the height is 13 centimeters. And the circumference, so again, that's another important vocab word. The circumference of the candle is 31.416 centimeters. All right, before I keep reading, I want to make sure I'm looking at my units. It's 13 centimeters, 31.416 centimeters. So right now I'm good. And then it says about how much wax to the nearest cubic centimeter. Centimeter, 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 they match, so I'm good to go. Cubic, keyword, tells me that I'm finding volume. Is going to be needed to make this candle. All right, I'm going to start off by just writing the volume formula of a cylinder because I know I have to find the volume eventually. So the volume is pi r squared h. Okay. On the side, you don't have to do this, but I hate when they don't give a picture. I always like to make one myself. So I'm just going to quickly create like a cylinder. It could look like a can of soup, can of soda, barrel of oil, anything like that. So there's my cylinder. And I know that the height of the cylinder is 13 centimeters. So I'm just going to add that on here on the side. This whole distance is 13 centimeters. If I want to find the volume, I don't only need the height, I also need to find the radius, which is something that they did not give me. They also didn't give me the diameter. I know the radius is half the diameter, so that's not really working either. The only other vocab word they gave was the circumference, okay? Just as a refresher, if you are walking the track at school, the track is in the shape of a circle, all right? If you walk the track from start all the way to the end, that distance that you're walking would be the circumference, all right? If you look at your reference sheet, you'll see, if you look up the shape for circle, they do give you the circumference formula. It's a C equals formula. There's two there. I'm just going to fill in the circumference equals pi d, just because I think it appears first, all right? So if they're giving me the circumference, I'm going to just plug in for that. So I can replace C, the circumference, with the 31.416. Pi is just a number, so I can bring it down. And then D is helpful because I know the radius is half of the diameter. So now I have to get D on its own, and then I'm basically kind of good to go here. So if I'm solving for D, I got to get it by itself. So the opposite of multiplication is division. So I'm going to just divide the pi out on both sides. So I'm left with just the diameter. So if you type this into your calculator using the pi button, you should be getting 10.00002,338. Okay, this is not a final answer, so I have to keep the whole decimal. But I don't want the diameter, I want the radius. So if I take this and I divide it by 2, I'm going to cut it in half, I should be getting 5.00011,692, something like that. All right. So on the side here, now I have the radius, and they already gave me the height from before. So I can plug in and kind of go from there. So volume is pi times the radius, which is this big decimal, 5.000011692 squared, times the height, which is 13. When you type that whole thing into your calculator, you should be getting 1021.0. And again, it says to the nearest centimeter. So I went around to the nearest whole number, which means I'm going to stop right here. That would give me 1021 centimeters cubed. Okay. And then last but not least here, if I go to example 4, as I'm reading, it says a carpenter made a storage container in the shape of a rectangular prism. So this is just out of habit. Anytime they name the shape, I always like to highlight it. They're telling you that it's 5 feet high. So I'm just going to highlight that in green. And it has a volume of 720 cubic feet. These are all important keywords. He wants to make a second container, which is going to have the same height. So he wants to make a second container that has the same height and volume as the first one. Only instead of it being a rectangular prism, he wants it to be in the shape of a triangular prism. So again, anytime they name a shape, I always like to highlight it. And then it says, what will be the number of square feet? Square feet. Anytime something is squared, I know that represents area. So I'm just going to write that. This really is telling me the area. As I continue reading, though, they're telling me square feet in the area of the base. I'm going to highlight that as well, in the area of the base for the new container. So basically the question is telling me that I had the first shape, and now I want to take that shape and kind of make it into a triangular prism instead, using these dimensions. All right. So I'm just going to start off by kind of labeling everything as I go. So I want to find what will be the number of square feet. So what's going to be the area of the new container. So the new container is in the shape of a triangular prism. So right now, the only thing that's important to me is the triangular prism. If I look up the volume formula, because they gave me volume of the rectangular, and I know that this will have the same volume again, so I might as well look up that formula. Volume of a prism is capital B times H. This is where it is so important. The reading of the question comes into play. The question says that I want to find the area of the base. Who remembers from the other few lessons what letter represents the area of the base? Oh yeah, you're right. It's the capital B. So I'm just gonna mark that right here. Area of the base is really the capital B. So if I want to answer this question, I'm really just finding what B is, and then I'm done. So if I look back one more time, they're telling me that this new shape, this second container, is going to have the same height and the same volume as the first. So I know the volume of the triangular prism. It's 720. And I know the height of this prism. It's 5. And now I just want to get B on its own and I'm done. So I just have to divide 5 out on both sides because the opposite of multiplication is division. So if I divide it away, I get 144 equals capital B. So what's the area of the base for the new container going to be? It's going to be 144 feet squared because it's telling me here the area is in square feet. So I'm just going to include that on the side. All right, you guys are rock stars. I hope that you, again, rewatch anything that might have seemed confusing. There was a lot going on here, especially in example 2. So keep up the good work and make sure you get that homework done and upload the entire lesson when it's complete. All right, have a great day, guys.